Yeah, next one is branch and bound. So the general idea here is given a specific classification task, again we are supervised with a target function, maybe accuracy, f-measure, precision, recall, whatever. The aim is to again select the k-best dimensions to learn the classifier. And now we assume that we have a monotonic j. Yeah, so the target function, the target function is actually the quality measure for the subspaces. So we now assume that this quality measure, the j here, is monotonic. That means for any two subspaces of the original feature space, where X is a subspace of Y, it holds that J of X is smaller or equal than J of Y, if J is maximized and if J is minimized the other way around. In other words, if you have a Y and you eliminate a feature, J can only get better. Yeah. The other way around, if you have something which is already bad, adding another feature to X, so if X is already bad or worse than another one, adding a new feature, so pumping up the feature space, pumping up X, will not make J better. Yeah? So J at best remains the same, but will not will probably decrease. Yeah? And that can be used to search bottom up, like the a priori or the FP growth algorithm from frequent item set mining, to find the best feature space actually. Yeah. So in that case, we start off with a full data set. So we use a top-down approach, not a bottom-up approach, but a top-down approach with the best with a depth-first strategy usually, and the nodes where the J values are smaller if it's maximized or greater if it's minimized, the current best solution need not to be explored, because we know that the monotonicity ensures that all children cannot be better than that what we found so far, which is just the consequence of the monotonicity. So here's an example. Let's assume that we want to maximize J. We start off with a 4-dimensional feature space, and we want to find a one-dimensional, the best one-dimensional feature, which is a little trivial because we will just evaluate each on its own. But anyway, yeah. So we just want to see how this top-down approach works here. So target dimensionality is 1. And we start off, of course, with a 4-dimensional original feature space having features A, B, C, D. So in the first step, we compute all the 3-dimensional subspaces of the original one here as candidates and compute the J values. So you see here, this one has a J of 1.0, blah, 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 blah. We want to optimize, so we use the best one here, which is the one which has we want to maximize, I'm sorry. So not optimize, of course, yeah, but what means optimize? We want to maximize the J score. So we continue with the one that has the highest J score, which is this one here, obviously. So in the next step, we expand this one here. So we get the 2-dimensional projections of this one here, which have only B, C, D. Yeah, so we have ZD, BD, and BC. And we can also again compute the J scores. Since we have not reached our target dimensionality, we continue with the best one here, which is this one here. So we look at the projections, the subspaces of this subspace CD, which is D and C. Yeah? And you see here that now we reached our target dimensionality, and we take the best one as the actual bound. So this one here is the best with one-dimensional subspace which we found so far. So we can immediately prune this one here, because this one is less good, not so good as this one here. Yeah? But we can also prune a lot of other things here. So we can prune, for example, this one here, because this one is already smaller than this one here. So this one cannot contain any one-dimensional projection which is better than this one here. Same holds true with this one here. Same holds true with this one here. And same holds true with this one here, because just the J values of those 4 things here, and this one too, is actually also already smaller than this one here. The best current solution we found so far. The only thing where something can happen is this one here, because this one has a J value which is already still larger than this one here. Yeah? So we have to expand this one and see, okay, the 2-dimensional projections here have J values that are already also smaller than this one here, so they cannot contain any one-dimensional projections that are better than this one here. So we found this solution here as the best one. Okay. Yeah, so the question is, how do those quality measures look like for the branch and bound algorithms? So there are different ones. So I want to show you one here, which is the subspace inconsistency measure, which is a very, very simple one, as you will see here on this slide here. It only works on best works for categorical data. So given a data set of categorical features, the idea is, if we have identical vectors u and v in a specific subspace, but having different class labels, this subspace is somehow inconsistent. Yeah? So vectors that have identical values, and so you see it only works for categorical data, or best works for categorical data. So if the categorical values of those 2 vectors are the same, but do not have the same class labels, something is inconsistent. Yeah? If the values are the same, the class labels should be the same. Yeah? And we can use this observation to measure the inconsistency of a subspace. So xr of u is the amount of all identical vectors u in a given subspace R, and this one here is the amount of all identical vectors u having already the same class label. So this one here is a subset of this one here, obviously. Yeah, and in the best case, those 2 sets are the same. In that case, R is completely consistent and should be kept. Yeah, so we can compute the inconsistency by relating this one here with the maximum of all those things here, because we have different class labels, of course. Yeah. In the best case, we have one of those sets equals, so those are sets, so the cardinality of one of those sets equals the cardinality of this one here, and the other sets for the other class labels are 0. Yeah, so mind this C here. Yeah, so in that case we have, for example, 100 instances minus 100 instances is 0. Yeah. So that is the inconsistency of the subspace regarding this specific vector. And now you can sum up the inconsistencies of all vectors in this subspace and normalize by the number of vectors here. Yeah? So this is the inconsistency score of a subspace, and this inconsistency score is actually monotonic. So if R1 is a subset of R2, obviously R2 must be at least as much as the inconsistency of R2 must be greater or equal than R2. R2. Yeah, because if you add something, the only thing that can happen is everything remains the same. So if you add something, means you go from R1 to R2. From R1 to R2, you add something. Yeah, you add some new feature. So in the best case, everything stays the same. Then it's equal. But you may expect that you add something which adds inconsistency. So in that case, it gets smaller, and the inconsistency of R2 gets smaller. Yeah, I think it's quite intuitive. So advantages here, short discussion. Monotonicity allows, of course, efficient subspace search, and you get the optimal solution then. especially the inconsistency score is very well suited for discrete data or binary data, yeah, because you count identical values, and that's not really working for very well working for real value attributes, of course. Limitations: useless without groups of identical values. Yeah, for real world vectors, you need to come up with groups of identical features. So is, for example, 3.5 and 3.7, is that does that count as identical features or values or not? So that's the question for real valued vectors actually. Yeah, and worst case runtime complexity, of course, remains exponential. So 2 to the power of n. Sorry, d is not the right letter here. That should be n, red n here, of course. Yeah. So worst case runtime complexity is still exponential in the number of features n.